So today we're going to work on oxidation states and identifying redox reactions. Hopefully we'll be able to answer the next couple of questions. So we have a couple rules when it comes to the oxidation states. The first rule is talking about free or uncombined elements. So the free and uncombined elements usually have an oxidation state equals to 0. So this includes things like sodium on its own. Sometimes you could also have something like magnesium on its own, but this also includes things that are like molecules naturally, things like oxygen on its own, chlorine on its own, or even sulfur that exists on its own in a ring of eights. So all these have an oxidation state of 0. And when we're talking about oxidation states, we're talking about the hypothetical charge that a compound has or that an element, atom, or ion has. Okay, and then your next one is talking about neutral compounds. So neutral compounds also have a or an oxidation state equals to 0. And by neutral compounds, I mean things that are composed of different types of elements, but then overall the charge is 0. Things like water, NaCl, um, maybe something like H2SO4. These are all neutral compounds because they don't have any particular ions or anything like that. So there's like, you can say it's a charge of 0, even though we never really write the 0 like that. Okay, and then your next rule comes down to your polyatomic ions. So the polyatomic ions, their charge is equals to their oxidation state. So if I have a polyatomic ion like SO4 2 minus, which is the sulfate ion, then the oxidation state of SO4 2 minus is going to be -2. Or another example is if I have the nitrate ion NO3, everything is going to be equals to -1 for the charge. So the charge we see in the little number at the top, that's going to be the same oxidation state. And then talking about main group elements, your main group elements, whatever charge you would predict that they would get from your previous knowledge, that's usually the oxidation state. And by that, I mean, let's look at our periodic table here. Group 1. Group 1 usually forms +1 charge. So that means that their oxidation states would usually be +1. Group 2 usually forms +2 charges. Then that means that their oxidation number will be 2. But then if we go into this area over here, these are your transition elements. And one thing about them is that they have variable oxidation states or oxidation numbers. We interchange the two. And then boron, that's group 3. So that usually forms +3. And then carbon and everything downwards in group 4, they usually form +4 charges, but in reality they can form anywhere from -4 to +4. So oftentimes we'll have to solve for what their oxidation state is. Group 5, they usually form -3, group 6 -2, group 7 -1, and then group 8 0. So main group elements are the ones that aren't transition elements. So that includes this one, this one, this one, this one, this one, this one, and this one. And so we are usually able to predict based off of their position in the main group what their charges would be. Okay, so let me go ahead and clean that out. All right, and then that's the rule for this. So refer over here for those rules. And then for the transition elements, we already know that they have the ability to form many different types of charges. So we usually have to solve for the oxidation number of transition elements. So something like Cr, they would say, what's the oxidation number of Cr in a specific compound? Well, we can't easily answer that. So we usually have to solve for it. And we're going to work on that very soon. But before we do the calculations for, unknown oxidation numbers, I do want to talk about a couple of exceptions. Metal hydrides. So these are hydrides that are composed of a metal and then you have a hydrogen. A common example of this is sodium hydride. So sodium hydride, sodium is +1. So Na is +1. And then hydrogen has to have a charge that complements sodium in order for you to get a overall charge of 0. So that means that hydrogen in this case is actually going to be -1, which is unusual. This is unusual because This is very unusual because we notice that hydrogen is in group 1, so it usually forms a +1 charge. So we will say that hydrogen in a metal hydride is unusual because it's normally plus 1. And then another instance that is unusual is peroxides, because normally peroxides, or normally oxygen is having a charge of -2. But in peroxides, we're going to notice is something different. The common example I like to use is hydrogen peroxide. And so in the case of hydrogen peroxide, we know that hydrogen, its oxidation state is +1. So oxygen, there's two oxygens. So that means that for this hydrogen peroxide to be neutral, oxygen has to have a charge of -1. And again, this is unusual because oxygen is a group 6 element that usually has a -2 charge because it's normally -2. Okay, so those are the exceptions. So now let's try doing a couple of calculations here. So if they want us to solve for the charge of Cr in Cr2072 minus, we can refer back to our understanding of what this is. So this is a polyatomic ion. The overall oxidation number is going to be equals to -2. And then we're solving for chromium, for chromium in this compound. So we're going to say Cr is unknown, but there's two of it. So it's going to be 2 times Cr. And then we have 7 oxygens. Each individual oxygen, this is not one of the exceptions. So oxygen in this case is going to be -2 as usual. So that means that we have 7 of the -2. The 7 came from the small number below oxygen, and then the -2 is the charge or the oxidation state of everything. So we know that all of this is meant to add together to give you a -2 charge because it's a polyatomic ion with a charge of -2. So if we were to do our calculation, it would mean we have 2 times Cr minus 14 equals -2, which is the same thing as 2 times Cr is equals to plus 12. So Cr is going to be equals to plus 6. So that means that the answer here is going to be plus 6. So we're leveraging the fact that we know that it's a polyatomic ion, so the overall charge is -2. And we're also going to leverage the fact that oxygen is known to have an oxidation state of -2 as well. So it's going to be plus 6. How about in another instance where they want us to solve for the oxidation states of carbon and ethane, which is C2H6? Well, let's give it a try. So in carbon or in C2H6, you have 2 carbons and you have 6 hydrogens. And this is a neutral compound, so everything is meant to add together to give you a neutral charge of 0. So that means you're going to do 2 times C, C is unknown, plus 6 times, well, what's the oxidation state of hydrogen? Hydrogen is usually having a charge of +1, unless it's in a metal hydride. In that case, it's going to be -1. But in this case, it's just your regular hydrogen, so it's going to be 6 times +1, and all of that is going to be equals to 0. So you're going to get 2C plus 6 is equals to 0. So it's going to be 2C is equals to -6. So C is equals to -3, which is, to be expected. That's normal. But then just remember that carbon is a group 6 or a group 4 element. So carbon is a group 4 element. So that means that it's normal for it to have a charge between -4 and +4. Okay? So in this case, our answer for number 2 will be -3. Okay? Then the next question, what is the oxidation state of H in H2O2, which is a peroxide? Well, let's do that calculation. We know that H2O2, well, this is hydrogen peroxide. And since we see this word peroxide, that means that oxygen has a charge of -1 instead of its usual charge of -2. So we can do that calculation. In H2O2, you have 2 hydrogens and you have 2 oxygens. All of this is giving you a neutral charge of 0. So you're going to say 2, and then H is what we're solving for. So 2 times H plus 2 times -1, that's going to be equals to 0. So 2H minus 2 equals to 0. Okay, and then that means that you're going to do 2H is equals to 2, and then H is equals to +1, which is the normal charge that we see for hydrogen. So the answer is going to be +1. Next one. Calculate the oxidation states of sulfur in H2S2O7. H2S2O7, well, that is a neutral compound. All of it is equals to 0. So we can go ahead and set up the equation. We have 2 H's, 2 S's, 7 O's. All of this is going to give you 0. So we're trying to solve for S. So that means that we can assume the oxidation state of oxygen and hydrogen based on our rules. H is a group 1 element, it has a +1 charge. O is a group 6 element, it has a -2 charge. So we can say 2 times +1 plus 2 times S, that one we're trying to solve for S, sulfur, plus 7 times -2. All of that is going to be equals to 0 because this is overall a compound that has a 0 charge. So it's going to be 2 plus 2S minus 14 is equals to 0. So 2S will be equals to 12 because it's going to be plus 14 minus 2. So it's going to be 12. And so S has a charge of +6 in this compound. So I can just go ahead and write +6. Last question. So solve for the charge of sulfur in sodium sulfate, Na2SO4. Well, I actually want to show you 2 different ways you can go about solving this. One way is if you know that you have Na2SO4, then you can kind of make a guess as to what the charge of sulfate is, because sodium is a +1 compound or +1 element or ion, and then sulfur or sulfate is going to have to be -2 so that they can cross their charges, and so you can get sodium sulfates. So you can actually kind of make an educated guess that SO4 as a compound or as a polyatomic ion has a charge of 2-. So if we know that, then we can say S plus 4 oxygen is going to be equals to -2. So sulfur, we're trying to solve for it, plus 4 times -2. All of that is going to be equals to -2. So S plus -8 is going to be equals to -2. So S in this case will have a charge of +6. That's one way we can solve this. or you can kind of deal with everything as if it were a neutral compound. So instead of focusing on just the polyatomic ion of sulfate, you could just kind of focus your attention on the whole compound as a whole. So let's try that one. So Na2SO4, this is a neutral compound. So in this case, in my calculation, I'm going to include sodium. So it's going to be 2Na, 1S, and then 4 O's. All of this is going to be for a neutral compound of 0. So you're going to get 2 times 1, or plus 1, plus S, plus 4 times minus 2. All of this is going to be equals to 0. So you're going to get 2 plus S minus 8 is equals to 0. So S will still be equals to plus 6. So you can kind of focus on calculating the charge of S just based off of what's in the polyatomic ion, or you can solve for the whole compound and equate it to 0 instead. Both ways you get your answer. And now that we've understood how to calculate oxidation numbers and the oxidation number rules, we do need to learn about what reduction is and what oxidation is. Okay, so going into that, if I want to say that something is going through oxidation, I'm talking about an increase in the oxidation state. So if the oxidation state was 0 and then it went to plus 2, or maybe it was plus 2 and then it went to plus 3, then I'm talking about an oxidation in this case. An example of this is, let's say I have iron and that iron wants to go through an oxidation and it becomes iron 2 plus. And then you're losing 2 electrons on the peroxide. Then because the oxidation number was 0 on the left-hand side because it was in its elemental state, and then it became plus 2 because of the charge of the overall ion, then I can say that there was an oxidation taking place. So that's what oxidation is usually about. And then reduction is talking about if there is a decrease in the oxidation number or the oxidation state. So an example of this is if I go from 0 to minus 2 or from minus 2 to minus 3. So it's getting more negative. So in this case, I'll end up just going through a reduction or a decrease in the oxidation number. So an example of this is maybe if I have something like this, chlorine gas, and then that one gains 2 electrons, and then I end up getting 2 chloride ions. So the oxidation state here is 0, and then the oxidation state here for each individual chloride is minus 1. So there is a reduction in the oxidation state, so I can say that this is a reduction happening. So in a typical example of an equation, you would usually have oxidation and reduction happening together. So that means that we would have a redox reaction. And so a redox reaction is one where oxidation plus reduction, both these things are happening. So you're seeing some elements going through, or some atoms are increasing in oxidation number, some are decreasing in oxidation number. So if we're able to look at an equation and see a change in the oxidation number for specific elements from one side to the next, we can say it's a redox. So an example, is this reaction you're seeing here, is this a redox? Well, let's see. This is for the combustion of methane. So we can calculate what the oxidation number is for the two different sides. So starting with carbon. Carbon, we usually need to solve for that because it's group 4, so it's pretty hard to determine. So if I want to solve for the oxidation state of carbon, well, I know for sure that the hydrogen should be a plus 1. Should be a plus 1. So C plus 4 times H. This is a neutral compound, so everything is going to be equals to 0. So carbon plus 4 times plus 1, which is representing the oxidation state of H, that's going to be equals to 0. So carbon plus 4 is going to be equals to 0. Carbon's oxidation state in methane is going to be minus 4. So this is a minus 4 over here. And then each individual hydrogen is a plus 1. And then oxygen over here. Well, oxygen, we're not dealing with the big number in the front. That's just for balancing. We're dealing with the actual species, which is O2. O2 is an element in its natural state or in its free state. So that means that it's going to be an oxidation state of 0 in this instance. And then going to the product side, I can determine the oxidation state of carbon by calculating once again. And then oxygen in a compound, when it's not in its free states, when it's part of a compound, you can always determine that it's usually minus 2 for oxygen. So it's a minus 2 for oxygen. So if I want to calculate for carbon, I'm going to say you've got two carbons, or sorry, you've got one carbon and then two hydrogens, or two oxygens, and that's going to give you a 0 charge because everything is neutral in carbon dioxide. And so you're going to get C plus 2 times minus 2 all of that is going to give you a charge of 0. So carbon minus 4 equals 0. Carbon's charge is going to be plus 4. And then in water, hydrogen and oxygen, they adhere to their regular rules. So hydrogen's charge will still be plus 1 in this compound, and then oxygen will be minus 2 in this compound. So let's look at what's kind of happening here. So we know the carbon here is going to be plus 4. So I'm just going to clear up this little space over here so we can do a comparison and see what is going on. So carbon to carbon, from carbon to carbon. Carbon on one side was minus 4 in methane, and then it went all the way to plus 4. So what does that mean? It means that there was an increase in the oxidation state. So that means that this was an oxidation taking place. Hydrogen was plus 1 on the other side, and then plus 1 on the other side as well. There was no change in the hydrogen, so we're not going to say it was reduced or oxidized. However, when we look at oxygen, it was 0 on one side, and then it became minus 2 on the other side in both the compound of carbon dioxide and water. So I'm just going to draw a relationship from here to here and say that it was a reduction taking place. So is this a redox or not? The answer is yes, it's a redox. Because we see that carbon got oxidized and then oxygen got reduced. Well, I hope that helps. And as usual, feel free to comment or message if you have any questions or have any concepts you would like to cover.